Choose wisely, Dave. You can't have another.
All right, hi. So, I forgot to give the internet sensation spiel as well.
Yeah.
They have a website with a blog that has awesome EE stuff on it you guys should check out. He's been about to write on the board for you. Some pretty cool stuff.
It is literally blog.thelifeofkenneth.com because I am Kenneth Finnegan. I am a mechanical engineer by training, having just transferred here as an electrical engineer because I thoroughly enjoy the concept of electronics, both from a theoretical point of view and a very applied practical point of view. So today I'm going to be giving a hopefully not too painfully long talk on as a survey into the various active devices. So I'm going to be talking about the diode, the transistor, and then all the various different kinds of transistors, and then I'll take at that point a breather break, and depending on how much time we have left, I'll then go into vacuum tubes of various of different varieties and different functionalities. And I'll try and give you guys kind of a very layman's-esque understanding of kind of how each of these things operate. Any of the EEs in the audience, obviously at some point you'll have to take a bunch of classes to learn all the math behind it. So I'm going to kind of skim over the math and just kind of do the conceptual understanding. All right. All right, so there, at any point, if there's any questions, just stop me, because, you know, I don't know what I'm talking about, because I'm just a lousy ME. Yeah. Okay, so let's talk first about the standard silicon diode. I'm going to pass around a little card here that has on it a various selection of diodes. Let's talk about what the basic diode does. Given a wire, the schematic symbol for a diode looks like this. And a diode literally means it is a one-way gate. Current can flow in one direction, and current cannot flow in the other direction. All right? Thanks to Benjamin Franklin for guessing wrong, unfortunately, while current is in this direction, electrons are moving in the opposite direction. So that's going to get really, really confusing, and I apologize, but blame Benjamin Franklin because he guessed wrong about which one was positive and negative, and so electrons are negative, right? The most basic application of the diode is as a power rectifier, right? So all the walls in your house have in them 60 hertz at 120 volts, which then is not particularly useful for any of your electronics. And so one of the most standard applications for a diode is having some transformer that you take 120 volts in, take 12 volts out, and then you put some various selection of diodes, and this lets current pass in, but not let current pass back out into the transformer, and you get a positive voltage here, right? Does this sound familiar, make sense to all of you, all right? There are a multitude of other applications of diodes, which are crazy and really complicated, but this is one. So this is just taking advantage of the simple fact that diodes can conduct in one direction. Another mechanism for using diodes is taking advantage of the fact that they have a kind of a fixed voltage. If you pass current through a diode, it has a fixed voltage across it, right? The ideal rectifier has no voltage drop at all. So we're going to say this is voltage, and this is current, which I'm just going to write I, current. All right? So on the x-axis we have voltage, and on the y-axis we have current, right? And so as we apply voltage to the device, the current will change, right? For your basic resistor, this is a straight line, right? Because this is your Ohm's law, where voltage equals the current times resistance. Change the resistance, this slope goes up and down, right? So that's your resistor. Your ideal rectifier is going to have 0 current whenever the voltage is negative, and then have infinite current when it's positive, right? So that is the ideal rectifier, because anytime you have a negative voltage, it doesn't let current flow back. And anytime you have a positive voltage, it lets as much current flow through as it likes. Unfortunately, while this is very interesting in your classrooms because professors love academic, idealized scenarios like this, silicon diodes don't behave anything like this at all. Silicon diodes instead have very, very small leakages in the backwards direction. We're talking microamps or nanoamps. So you can usually ignore the backwards leakage, but in the forward direction, instead of it going straight up, the diode doesn't start conducting until you forward bias it at something around 0.6 to 0.7 volts, right? So various people will say, hey, the forward bias voltage, which is the voltage across the diode when it's conducting, is 0.6 volts or 0.7 volts. And you'll always hear these different numbers because it's really not necessarily all of them. Is this, depending on how much current is flowing through the diode, the voltage across the diode is actually an exponential function, right? You can usually, for most practical purposes, just assume that it's about 0.7, but that's another simplification. And so this will turn out to be problematic as I get into more advanced devices. But just appreciate that this isn't necessarily, this is still not even a sharp corner like your professors will maybe admit in your electrical engineering courses. So that is the diode. All right, let's talk about how the diode actually physically works. All right, so now we're going to be dropping down into the concept of semiconductors. All right, so the diode is a two-terminal device. So here's our diode, and it is going to be some chunk of silicon that is divided into two regions. We have a P section and the N section. So what I mean by P and N is this is one silicon crystal. So we've grown a crystal out of silicon, and then we have, in very controlled quantities in the two regions, added other elements to change the electrical properties of the silicon. In a P semiconductor, we have added positive elements. So this is elements that have less than 4 electrons in their valence, if any of you paid attention in chemistry. And then in the negative half, we've added elements that have more negative charge than silicon, right? And so in their natural state, so if you just take a hunk of N semiconductor, there's going to be a tendency for it to have extra negative charge just in it, right? Which is really hard to grasp and something that you kind of never really understand at a useful level. So if this is confusing, congratulations, you're paying attention. In the positive section, you have positive charge. Unfortunately, as Benjamin Franklin got wrong, the positive charge is a proton. Protons don't tend to move around. So when I say positive charge here, I don't mean that there's actual protons moving around. I really mean that there is lack of electrons, right? So when I say a positive charge here, it really is kind of like a bubble in the aether of electrons that is the semiconductor, right? Which is practically not very important, but is nuance of the actual chemistry of it, right? So when I say positive charge, I mean lack of electrons. When I say negative charge, I mean excess of electrons, right? Positive charges and negative charges really like each other and they attract towards each other, just as magnets, north and south poles of magnets attract each other for practically the same reason. When a positive charge and a negative charge actually touch each other and meet, they cancel each other out and disappear. So if you think about it, since we have positive right here and negative right here touching each other, they are intrinsically, like, these positive charges are getting attracted to the negative charges and want to cancel out with that. All right? But the P semiconductor needs to intrinsically have this positive charge. And so what happens is positive charges start to migrate to the negative side and cancel each other out. But after they get canceled out and become a neutral semiconductor in that center region, the N and P semiconductors start recreate their original charge. Luckily, this eventually reaches an equilibrium, and you end up with this section in the middle where the charges are created and cancel each other out at an equal rate. And so this is called the depletion region of the diode. So what this means is there's no positive charge and no negative charge in the center depletion region, and it's instead a non-conductive region. All right? This is why diodes do not conduct, right? If we now apply a voltage here, so if we apply a positive voltage here and a negative voltage here, which I'm going to represent by a ground and arrow up, we're going to start adding more positive charges on the P semiconductor and more negative charges on the N semiconductor, because the positive side is adding positive charge and the ground is adding negative charge. By exerting force, this electromotive force on the depletion region, we start to move this depletion region in and we make it narrower. Does that make sense? Raise your hand if that makes sense. Okay. So by adding more positive charges to the P semiconductor, we make this depletion region not be able to keep up as much with canceling out these charges. Since the charges are actually sitting here and canceling each other out, that's why there is still down here a very small leakage. Not much leakage, but a very small leakage. And also why there is a small leakage in the opposite direction. Because even if we apply a positive voltage over here, the depletion region is going to prevent current from flowing via just normal conduction. But this depletion region, intrinsically in it, has this charge cancellation, which does allow some negative charge to move in the wire, move into the depletion region, get canceled out by a positive charge over here, and then, effectively travel through it. So that's why leakage currents happen. All right? But we don't want leakage current, because leakage currents are really small and not very useful. So we want this diode to actually conduct as a full conductor. To do that, we need to apply enough force to this center depletion region to shrink it to the point where it finally meets itself. The P and the N sections actually finally meet each other, and the depletion region completely disappears. This is why the diode junction has a 0.7 volt, 0.7 volt voltage drop across it. Is the force, this recombining force that creates the depletion region, has an equivalent voltage of 0.7 volts, kind of. Right? Because it's not actually any single value. As you pass more current through it, if you pass just enough current through it to get rid of this depletion region and you have, charge moving through and everyone's happy, you're still going to get little pockets of depletion region, which are then going to get canceled out again. That is why the voltage, that's why as you apply more voltage, all of these trace bits of the depletion region get really wiped out and you get even higher current, right? So that is the diode, right? If we instead reverse it, so now we're applying a positive voltage to the N semiconductor and a negative voltage to the P semiconductor. So this side, the voltage is higher than this side. we are now drawing these negative charges out through this wire. And we are drawing the positive charges out through this wire. Because we're equivalently putting negative charges in and putting positive charges in. Which is confusing, right? Because positive and negative are opposite. We can talk about current in whichever way we want, be it the movement of positive charge or the movement of negative charge. When we have the diode just sitting there, we have the 0.7 volt depletion region in the center here. As we apply this electric force to it in the opposite direction, this depletion region instead grows, right? But the fact that it grows isn't particularly important. As long as it still exists, there is no current. So that is why diodes only pass current in one direction and not the other. Of course, if we keep applying a larger and larger reverse voltage like this, eventually the entire semiconductor gets depleted, and we instead just have a piece of silicon, right? We're talking on the order of microns here. This is a tiny square that I'm drawing for you guys, because I don't happen to have a good microscope, so I'm not actually going to show it to you firsthand. Once you reach this point, the diode is eventually going to break down. Because just as you can take very, very high voltage and get it to arc across air, because even though air isn't a conductor, you can make an arc in air, you can eventually, with enough force, pass current through this. And this is called the reverse breakdown voltage of the diode. So in the positive direction, between about 0.6 and 0.7, we have this conduction. In the negative direction, we eventually have this breakdown where the semiconductor no longer prevents current flow merely by the fact that we're applying a ridiculously high voltage to it. And this is on the order of anywhere from 5 volts to 1,000 volts. The two most common diodes that you'll see are going to be, well, the most useful one for the power application I talked about is going to be the 1N4002. So this is the actual part number for the diode that is a 100 volt reverse voltage. And the 4000 is actually part of a series. It goes from 4000 to 4007, which are various steps from 50 volts up to 1000 volts. So that is a good power diode, which exhibits this response. But you don't always care about this part, right? You know, this is useful when you're dealing with high voltages like in your wall, but sometimes you don't really care about that, and you only really care about this part right here, and that's more important. And that's called a small signal diode. Because a power diode is useful over there, because it blocks a tremendously high opposite voltage. Small signal diodes only are so interested in this small section here and are most useful just because of this need for various reasons. Part numbers for that are going to be your 1N914, which is equivalent to the 1N4148. Because these are effectively both the exact same diode, they just have different part numbers. What these part numbers are coming from is that back in the 50s and 60s, an American organization called JDEC was smart enough to say, hey, all of these different manufacturers are making all these different semiconductors. We need some reasonable way to number them so that we can know that the 1N914 from one manufacturer is the same as a 1N914 from another manufacturer. Is it okay if I erase this stuff? Which then begs the question, why in the world did they come up with this 1N number notation. This number here is a totally arbitrary and meaningless number that was just sequentially issued. The first diode was the 1N1, and the latest diode is 1N and then a very large number. I've seen stuff up in the 6,000s, I think, but I mean, again, every single day, some manufacturer is coming up with a newer diode, which then leaves us with this 1N at the front. This nomenclature of the 1N, then the part number, actually originated in the numbering of power vacuum tubes. Is in vacuum tubes, you would have a filament, which would need some sort of power, and then you would have a type of vacuum tube, which would have some various number of screens of control grids on it, and then you would have the plate around it, which I'll get to after the break. But the 1 in vacuum tube land means the heater for this device is 0 volts, so it doesn't have a heater. Obviously, diodes don't have heaters, so yeah, it's going to have a 1 as its heater nomenclature. The N signifies that the diode is a crystal detector, because the diode was literally originally you would go find fuses of ore, and then you would probe it with a needle and try and find a good spot that happened to diode. So originally this meant no heater, crystal detector. As you'll see once we get into the transistor, eventually this number got reused. Instead of it meaning that this has no heater, this instead means a diode has 2 leads, where a transistor has 3 leads. Transistor has 3 leads, and that's why it says 2N, right? Fun little piece of trivia. Why they didn't go with 2, 3, and 4 was because of poor foresight and the fact that your professors hate you. All right. So those are your standard diodes. I personally, when I'm building a project, will usually, instead of going for the 4002, just always go for the 4007. I think the card that I was passed around had the 4002 on it. Back in the 60s and 70s, it mattered because the price difference between a 4002 and a 4007 was significant. Now it's actually usually cheaper to buy the 4007 because more people use it. So a lot of this stuff you'll see was only important because of how tremendously expensive semiconductors were at the time, but they are no longer that expensive. So 1 in 4002, and then this is your small signal diodes. I also, 20 minutes. Another sort of useful diode is called the Zener diode. Remember how the 4002 breaks down over there? You can actually, via very careful manufacturing characteristics, you can control at what voltage this breaks down. Right? Because if we can sit here and we say, I want this diode in reverse direction, not to break down at 1,000 plus volts, but to very specifically break down at 5.6 volts. And I believe that's the 52 series. Yeah. So there is a whole series that starts with a 5 and then a 2 and then 2 more numbers that give you every single voltage from from 1 volt up to several dozen volts. This is called a Zener diode. Zener diodes are very useful as a voltage reference. If you want to build a voltage regulator, you need some reference to then regulate against. I'll show this later, but essentially, if you have just some high voltage and then a Zener diode, and we say that the breakdown voltage of this diode is 5.6 volts, or 5 volts, or 3.3, or whatever, the voltage here, compared to here, is just always going to be 5.6 volts. Right? Again, this may seem totally abstract at this point, but eventually you'll realize if you actually try and build something, you'll find uses for this that are nice. And that is the diode. Any questions on the diode? Yes?
So it doesn't drop more than 5.6 in that direction?
If you were to apply more than 5.6, the current would exponentially grow, and either, that's why we had this resistor here, so if we apply 10 volts here, current would start to flow through this diode at 5.6, and so we'd have 5.6 volts here, and then we'd have the 4.4 volts left just across the resistor. Again, it's an exponential growth, and so if you don't design the rest of your circuit correctly for this voltage reference, you will very easily explode the diode, which is unfortunate. So that is the diode. The next sort of semiconductor is not one NPN junction like in the diode, but two PN junctions, and that's called a bipolar transistor. The schematic symbol for this is hopefully fairly familiar to you since you passed the technician's test for our sensors. So this is the NPN transistor. It has three terminals: the emitter, the collector, and the base. When I say emitter, collector, and base, does that mean anything to anyone here? Cool. Do you know why it's actually called an emitter, collector, and a base? Cool. All right. Conversely to the NPN is the PNP, which is almost the same schematic, except instead of being an arrow out on the bottom, it's an arrow in on the top, and the naming is backwards. The top one is the emitter, the bottom one is the collector, then the base is still in the same place. All right, let's talk about what the transistor does. The simplest model for a transistor is that it is a current amplifier.
As opposed to an old amplifier?
Yes, out-of-date amplifiers are not nearly as useful as current amplifiers, such as this one. So, given an NPN transistor, from the base, you pass a small amount of current through the emitter. Right? So this would be your audio signal, this would be the signal from your microphone, this would be some very small signal. This small current then causes a very large current from the emitter, collector, sorry. So small current from the base to the emitter causes a large current from the collector to the emitter. And this is called the HFE of the diode. So HFE, which you'll find in your data sheets for whatever transistor you pick, is going to equal the current from the collector to the emitter divided by the current from the base to the emitter. People really like to design circuits based on, well, look, here's the HFE, so if I put in 1 milliamp, I'll get X number of milliamps out of it. This is unfortunately a really bad way to design circuits because semiconductors are a very random process. When you actually physically take a silicon crystal and try and grow these N and P junctions in it, you have no, we can't really control it. Right? This is like baking cookies. You can look at the cookies and you can say, I think I need to cook it a little bit longer, but you don't really know if the cookie's good or not until you actually take it out and bite into it. So if you look at a data sheet,
You gotta fight these guys.
yeah, so
That's a good idea.
please don't try and don't. If you look at the data sheet for any typical transistor, these ratings are going to span an order of magnitude. right? So given your standard transistor, we're talking 30 to 300. And this means that any individual transistor that you pull out of your bag is going to have some gain somewhere between these two values, and we don't know what it is. All right, so that's a problem. That's why negative feedback is good. So once you get to your amplifier classes, they'll talk about negative feedback. This is why. Because if we try to depend on it being always 300, it'll never work, because it'll never always be 300. But let's talk about why this current gain actually happens, and why they're called an emitter, a collector, and a base. So we're now looking sideways onto a silicon crystal. So this is free air up here, and this is our silicon crystal. Now, as a manufacturer, how you make a semiconductor is that you lay down some sort of resist. You then remove it in the places that you want to do something, and you then bake this wafer, and you grow down into the silicon whatever you want to add. This is called photolithography, because you would do it via photos. Did anyone ever play with like bluing paper when they were little? It was this blue paper that you could put objects on and leave out in the sun for like 10 minutes. It would bleach super fast, and you'd have like this blue outline. It's exactly like that, except instead of it being blue paper, we're talking about the actual silicon crystals. So what you do as a manufacturer is you mask off the wafer, except for this one section. You then put it in an oven in a atmosphere that is tainted by some negative element, and you grow a fairly large region of N semiconductor. You now wash the resist off, reapply a new resist, and instead of it going all the way out there, you have the resist happen to go a little bit farther in. You now take the same wafer, you put it in a different oven that is slightly tainted by a positive element, and you grow a positive semiconductor. Now, once you finish with that, you take it out, you wash it off, you apply a new mask, third mask here, and you grow an N semiconductor. And instead of it being in a slightly tainted atmosphere, you really grow an N semiconductor. This is hella N right here, right? And then you wash all of the resist off. You take the whole wafer and you cut it into a bunch of tiny little squares. And then if you need, you then take each one of those little squares and you put it in some sort of package and sell it to schmucks like us. So I have here my personal collection of practically every single different kind of case that I've managed to come up with for transistors. So please don't lose any of these, because some of these are incredibly hard and rare to find. So this is the topology of an NPN transistor. A very strongly doped N section, a P section, and an N section. In between each one of these junctions, just as we talked about on the diode, you're going to grow, or there is going to happen, this depletion region. Right? Because the positive charges and the negative charges are going to combine against each other and cancel out. Right? This, right here, is the emitter. So this is lots and lots of negative charges right here. This is the base, and then this is the collector. Now, in the NPN transistor, you're going to apply a very positive voltage to your collector. This means that this depletion region right here is going to grow fairly wide and is going to not conduct. On the emitter, you instead apply a positive voltage. No. On the base, you then apply a positive voltage relative to the emitter. Right, so we are talking here so this is some positive voltage some less positive voltage. And then this is a negative voltage. So by applying a small voltage here, we are eliminating this depletion region. Right, so that depletion starts to shrink until at 0.7 volts, that depletion region disappears. And now current can flow from the base to the emitter, which remember is actually electrons flowing from the emitter to the base. Because screw you, Benjamin Franklin. When this depletion region is gone, and because this semiconductor is very strongly doped, there is a ton of negative charges here that want to go somewhere. And so literally, the emitter starts, once you get rid of this depletion region, the emitter shoots electrons like a gun, right? It just starts gushing electrons any which way it can. And because we've formed this semiconductor in this nice bowl shape, the vast majority of those electrons, as they get shot through this P section, which is all depleted at this point, they eventually strike the collector and are collected. Just blew your mind, didn't I? So they strike the collector and are collected and effectively then cause current to flow from the collector to the emitter. This shooting of electrons is in almost no way related to base current, except that this collector emitter current depends on the base emitter current to continue to cancel out this depletion region here. Right? Because as you have negative charges flying randomly through this P section in the middle, you will inevitably get rid of this depletion region because you're having positive and negative charges cancel each other out. So you're going to recreate the depletion region, it's going to stop. So that's why it's characterized as a game. Small current from the base to emitter gets rid of this depletion region and maintains the removal of this depletion region, and then a relatively large current flows through. I always hate it when people say that the PNP is just opposite, but the PNP is opposite. So instead of growing a large N, a medium P, and then a small n, we grow a very strong P, a moderate N, and then a moderate P. This is still called the emitter. This is still called the base, and this is still called the collector. You can now see why, when they switch from NPN to PNP, they switch which side the emitter and the collector are on. Because now we're dealing with positive charges. So again, we have this depletion region here, but once we apply a small current from the emitter to the base, which is really electrons moving from the base to the emitter, because Benjamin's making stuff. Once this depletion region disappears, we now start shooting positive charges randomly, and they all get collected by the collector, right? So while the NPN is a small base emitter current that causes a large collector emitter current, the PNP is mnemonically a small emitter base current, which causes a large emitter collector current. Profound. Does this make sense to anyone? All right, cool. So I've only lost a few more people. All right, so let's talk about what you could actually, so now you've like, hey, this amplifier thing is kind of cool. I actually want to use a amplifier in one of our circuits. So if you go to catalog and ask for a transistor, they're going to look at you like you're crazy because you need to specify which transistor you want. Like I explained for the diodes, there is a naming convention for them where they always start with 2, or will often start with 2N. And this 2N is a naming convention from the US. In Europe and Britain, they use their own numbering system, which is why if you ever find schematics from Europe, they'll always use transistor numbers that start with BC. And I can't happen to tell you why that is. But your real standard jelly bean transistor series is going to be your 2N3904, which is an NPN, your 2N2002, and your 2N3055. So these are just kind of progressively going up in power. So in the box I passed around, the little ones on the left are going to be your 3904s and your 2002s, 2222s, and then on the right side where they get super big and beefy, you start having higher power levels, right? So again, this is that signal versus power differentiation. But on the PMP side, you would have the 2N3906, 2N2907, and there's some power PNP, but that's less commonly used, so I can't tell you off the top of my head what that one is. But really, it's one of these things where when you want to find one of these, you either A, come find me and ask me, because I love helping you guys building this stuff because I'm the projects coordinator here. Or you also will go to some website like DigiKey or Mouser. DigiKey is your friend.
DigiKey is my friend.
And what is Mouser?
And Mouser is another website like DigiKey. These are two websites that you can go to, and they sell components. We're talking millions of components. So if you go to DigiKey's website and you go down to, I want a single transistor, it'll start asking you all sorts of questions about how much power you want to be able to deal with, and how much current you want, how much gain you have. And eventually it'll present you with this list of a couple hundred different types of transistors, and you'll just kind of pick the one that's cheapest. Right? So this is a bipolar transistor, which is the most traditional sort of transistor, and is actually fairly easy to make, and was one of the earlier technologies that they used to make semiconductors. Of course, in their infinite wisdom, scientists decided not to just invent one way to use semiconductors to amplify things, but many, many different ways. They kind of all divide into two categories. Your bipolar junction transistors, like this, and your field effect transistors. Which instead of it, oh man, I just erased it. Instead of it being, the gain being based upon the removal of that depletion region via the current through the middle, as you can see here, field effect transistors instead depend upon the static electric field being applied to a semiconductor to create or destroy that depletion region. All right. Let's talk about the MOSFET. This is the metal oxide semiconductor field effect transistor. Topologically, it looks like this. We have a semiconductor, we have a silicon wafer, we have an N channel here, something non-conductive like alumina or a ceramic or metal oxide, and then we just have a conductor up here, which is metal, right? So we have metal here, an insulator. So this is like, it could be plastic, but that'd be ridiculous. So it's a metal oxide because oxides aren't conductive. And then here we have a channel of the semiconductor, which is usually N, just because N semiconductors are easier to make than P semiconductors. But again, that was a thing that was a problem in the past, but is no longer, which is why N's always seem to dominate P's, even though there's no price or performance difference anymore. On one side of this connection, the other side of the connection, you have these two terminal connections, right? So these are your two wires, and the third wire is there. The schematic symbol for this you have your gate, your source, and your drain. Again, thanks to Benjamin Franklin, the mnemonics for source and drain are very confusing in that the source is negative on an N-channel MOSFET, and it then is the source of electrons that then flow through the MOSFET to the drain, right? Much like a faucet is the source that then runs to the drain. Benjamin Franklin, like, there was a 50-50 chance that he got it wrong. So, this gate here is so profoundly close to this semiconductor that just by applying a voltage to it, we can affect this semiconductor. Have any of you ever done the thing where you stand on the plastic box and you put your hand on a Van de Graaff generator and all your hair sticks up? Exact same principle, but instead of it being thousands and thousands of volts, we're talking, 1 or 2 volts. And instead of it being hairs here, it is, microns or fractions of microns. By applying a positive voltage on this metal, we positive voltage is going to attract. So by applying a positive voltage here, we're going to attract negative charges to it because positive attracts negative. And we're going to grow this channel of N semiconductor. Channel gets bigger, it can conduct more. If we instead apply a negative voltage to this piece of metal up here, which is the gate, we can shrink this gate to the point where it'll stop conducting. Right? Ask oneself, why the heck do we care about this if bipolars work perfectly well? The advantages of a MOSFET over a bipolar transistor is that the gate doesn't take any current. It's a very high resistance here, and so while a bipolar is expressed as a current gain, which is the output current over the input current, MOSFETs are instead expressed as a transconductivity, which is a output current over an input voltage, which profoundly is the inverse of resistor, which is why it's called a Mo. It's ohm backwards. Isn't that clever? Yeah. So that's a MOSFET. Advantages against the bipolar transistor, the input resistance of it is profoundly high. We are talking megohms or gigohms, right? And so this doesn't affect the circuit you're looking at compared to a bipolar transistor, which draws current out of it. So that's a MOSFET. A sibling to it is the JFET. The JFET, instead of it being this metal oxide separator here, it's instead a PN junction. I didn't want to put that there. N, and then a P junction. Again, we have gate in the middle, drain, and source. And then by varying the voltage on the gate, we can grow or shrink this depletion region, which then grows or shrinks this channel, and we can cut off or increase the current flowing through this JFET, right? Advantages of the JFET over the MOSFET is that it's much, much more robust, right? When we're talking about a microscopically thin layer of insulator here, the static voltage of your hand touching the table is enough to break down this insulator, right? Which then ruins the MOSFET. That's why every single piece of electronics you've ever bought, like a hard drive or a graphics card, always comes in those light gray bags that have all the warning stickers on them, ESD, sensitive material, blah, blah, blah. It's because these very, very thin gates are very easily destroyed. On JFETs, on the other hand, since it's just a silicon junction, silicon junctions are very robust because, you know, it's a silicon junction. Like, the worst that you can do is make it conduct. Like, literally, to destroy a silicon junction, you have to heat it up like 200 or 300 degrees Celsius and then pass a lot more current through it and have it thermally take off. So much harder to destroy. The disadvantage, on the other hand, is that we're depending upon this depletion region being here. If we apply too positive of a control voltage to the gate, this depletion region will eventually deplete, go away, and then this transistor will literally turn into a diode, which is problematic, but also gives you a bunch of advantages. Other than that, it's the same principle. You get applied voltage grows and shrinks there. All right, so that's a JFET. In addition to the MOSFET and the JFET, there is a multitude of other FETs: TFETs, NFETs, PFETs, RunFETs, CoFETs, Boba Fett. But none of those are particularly as interesting as these. Good example of the JFET is the MPF 102, and of the MOSFET is your 2N 7000. So again, if you wanted to use one of these in a project, you would use one of those two part numbers. At this point, since I've been talking to you guys for 45 minutes, we're going to take a breather for a few minutes, and then I'll come back, and having explained to you how transistors work, I will start all over again with vacuum tubes. Hopefully be half as boring.